As you watch this, one of Europe's most perilous volcanoes is quietly disintegrating, and it's not just minor cracks appearing. The entire side of the mountain is gradually slipping into the sea. Shockingly, scientists warn that this process is quickening. Sensors scattered across Etna's slopes detect unsettling activity. On its southeastern flank, a colossal boulder weighing billions of tons is detaching from the mountain. Initially, this movement was merely millimeters annually, seeming insignificant. Yet over the past decade, the rate has surged tenfold, with some regions shifting by a centimeter each month. What was once a slow landslide is now a catastrophic slope collapse. The implications of such a collapse are dire. When vast volcanic sections like Etna's front fall away, they send enormous masses of rock plunging into the sea, displacing vast quantities of water and generating monstrous waves, tsunamis, that can reach heights of 10 meters. Within minutes, coastal cities could be submerged, and the wave energy would propagate across the Mediterranean, threatening Greece, Malta, and even North African shores. The tragic reality is that these destructive waves could arrive with little warning, leaving populations unprepared. But what factors drive such a massive mountain disintegration? Every bit of ground movement escalates the risk of a more violent eruption, making future activity increasingly unpredictable. Since this slope is shifting toward the sea, scientists are growing alarmed that a significant collapse could trigger a regional tsunami, wreaking havoc along entire coastlines. Evidence of ongoing destabilization accumulates monthly. In 2018, researchers from Germany and Italy took a groundbreaking step. They installed specialized sensors on the seafloor beneath the island at depths exceeding 1 kilometer. Their findings shocked them. Both the surface and the deep base of the structure were sliding seaward. This indicated that gravity and magmatic pressure work together to weaken and destabilize the mountain's foundation. Since that time, seismic activity along the slope has intensified, not randomly but as stress cracks form. Signs of an impending disaster. Satellite radar imaging reveals deformation patterns consistent with early signs of a major eruption, emerging not from the summit but directly from the mountain's side. Historically, this kind of flank failure has led to catastrophic eruptions, such as Etna's most destructive event in 1669. On that occasion, the southern slopes suddenly trembled with deep rumblings, and without warning, the earth tore open kilometers below the summit, near villages. A relentless flood of lava erupted from the fissure, consuming everything in its path and vastly altering the landscape. This pattern underscores the danger looming beneath Etna's slopes, where ongoing structural weakening could soon culminate in a devastating collapse, unleashing destruction not just on the mountain, but across the entire Mediterranean basin. The eruption persisted for 4 months, devastating over a dozen villages and reaching the city of Catania, where homes, churches, and roads were buried beneath a shimmering ocean of molten rock. Recent months in Etna's activity have raised concerns, suggesting the possibility of a similar event rekindling. On June 2nd and 3rd of this year, Sicily experienced a dramatic episode that unsettled all observers. A powerful eruption erupted from the southeastern crater, which partially collapsed, unleashing a series of violent explosions. Ash soared several kilometers into the sky, while streams of scorching lava traced down the mountain slopes. Videos capturing these moments quickly circulated online, showcasing a spectacle both mesmerizing and frightening. Authorities promptly heightened the aviation alert status and restricted access around the summit to tourists, while the nearby ski airport periodically shut down due to ashfall. Despite the intensity, experts assess the eruption as relatively contained, with lava confined within natural barriers of the volcano. However, a curious pattern emerged. Seismic tremors rippled through neighboring towns, causing tourists on the slopes to evacuate en masse. Yet Etna itself remained restless. During July and early August, activity intensified, marked by frequent explosive bursts from various craters that sustained lava flows. Satellites detected significant thermal anomalies, and cameras monitored the ongoing eruptions continuously. By mid-August, a new phase of heightened activity was observed. Explosions grew more powerful, short-lived lava fountains erupted, and fresh cracks appeared along the slopes. Then a development occurred that heightened scientific caution. If you follow these topics, you might be interested to know that there is a Telegram channel dedicated to such content. There, we share exclusive satellite images, insights from analysts, and reports on strange and dangerous phenomena, material that for various reasons doesn't appear on other platforms. These updates encourage reflection on the ongoing geological processes shaping our planet. The link to join is provided below the video and in the pinned comment. Between August 20th and 23rd, a new lava flow branch opened on the flank of the southeastern craters, captured by drones and geologists observing an expansion of the active zone. Officials again restricted access due to lava reaching lower altitudes, with reports of ash deposits and intensified ash emissions along roads. Satellite data confirmed an increase in thermal activity, indicating that the eruption's force was growing stronger. Another escalation took place around September 22nd. Explosive activity surged, prompting aviation authorities to raise alert levels once more. The eruptions involved ejections of distinctive volcanic material and produced nocturnal lava fountains visible from the coast. Scientists also studied samples from a unique eruption that occurred roughly 3,930 years ago, which involved the ascent of a rare peckrate basaltic magma. Deep beneath the Earth's surface lies a rare and primitive form of magma, whose explosive potential is significantly underestimated. One such eruption, classified with an explosivity index of 4, resulted in catastrophic consequences. To put this into perspective, the 2010 eruption of an Icelandic volcano with a difficult-to-pronounce name, which disrupted air traffic across Europe, was of a similar eruptive intensity. Scientists studying ancient geological layers uncovered tiny mineral inclusions embedded deep within solidified deposits. These inclusions, microscopic fissures filled with molten material, serve as natural time capsules, capturing snapshots of the planet's fiery interior from thousands of years ago. By heating these inclusions under extreme pressure and temperatures reaching around 1330 degrees Celsius, researchers made a remarkable discovery. The original magmas contained up to 1% carbon dioxide and 6% water. These are extraordinary levels that suggest a significant role for volatiles in volcanic processes. The question arose, where did such abundant carbon dioxide originate? Previously, it was believed that carbonate sediments, deposited in ancient marine environments and lying beneath volcanoes, supplied the CO2. These sediments, melting under heat, could release gas into the magma chamber. However, recent studies challenge this notion, indicating a different source. Evidence now points to mantle-derived carbon, potentially originating from subduction zones where tectonic plates converge. This implies that the carbon was sourced directly from the Earth's deep interior, well below the crust, from depths exceeding 30 kilometers. right at the boundary where the Earth's crust transitions into the mantle. Such findings confirm the magmatic origin of magma under Mount Etna. What mesmerized scientists even more was the timing of magma ascent. Through sophisticated mathematical modeling, they established that the journey from the mantle to the surface can take as little as 2 to 3 hours, with some instances reaching up to 5 days. The final segment, covering the last 15 kilometers, occurs at breathtaking speeds, roughly 1 kilometer per minute, or about 17.5 meters per second, comparable to a projectile shot from a cannon. The driving force behind this rapid ascent is the extraordinary concentration of carbon dioxide and water in the magma. These volatiles create immense pressure, propelling the magma upward with explosive force and leading to catastrophic eruptions. Of even greater concern is the possibility that conditions conducive to such explosive events might be developing today. Current studies reveal that certain volcanoes, notably Etna, are emitting unprecedented amounts of CO2, about 10% of the entire modern global volcanic carbon output. This amounts to roughly 9,000 tons daily, 3 times higher than emissions from Hawaii's Kilauea volcano, which erupts in significantly larger quantities of magma. The source of this elevated emission rate was uncovered through analyzing the ratios of rare elements in the magmas of 4 regional volcanoes. It turns out that Etna's magma features exceptionally high concentrations of neodymium relative to tantalum, a signature that sets it apart from other active volcanoes of its type. All these findings underscore both the incredible forces shaping our planet and the potential risks that current geological activity may pose. Beneath southern Italy, particularly around Sicily, lie regions of the lithospheric mantle remarkably rich in carbon. These zones, situated roughly between 50 and 150 kilometers beneath the surface, are gradually brought to the surface through tectonic activity, specifically due to the rollback of the Ionian subduction slab. In essence, tectonic forces continually drag new sections of carbon-laden mantle underneath the volcano, possibly contributing to an increase in global carbon dioxide emissions in the future. Beyond its periodic lava fountains and eventual sliding into the sea, Mount Etna exhibits another peculiar feature. Its crater is in constant motion. Unlike typical relatively stable volcanoes, Etna's main vent seems to drift over time. Since the 70s, the southeastern crater has been regarded as the primary vent, but it migrated southeastward in 2007, and by 2011, it shifted again by just a few meters. The question of why this happens puzzled scientists until they studied 6 eruptions from 2007, leading to a breakthrough. By analyzing the density of rocks around the vents through satellite data and geological excavations, researchers uncovered that the rocks on the mountain's northwestern slope are notably unstable. These rocks often slide downhill, forcing the vent to migrate. This phenomenon correlates with the significant increase in Etna's eruptions during the latter half of the 20th century. Each new eruption deposits fresh lava atop the summit, adding more pressure to the slopes and provoking the observed movement. This brings us back to fundamental gravitational principles. For decades, scientists believed that volcanic activity was primarily driven by magma chamber expansion. As magma accumulates, it exerts pressure on the chamber walls, eventually causing an eruption when the walls give way. While this model explains many eruptions, some volcanoes like Etna challenge it. To probe deeper, in 2018, researchers installed underwater transponders on the southeastern flank, facing the sea, equipped with pressure sensors. These devices monitored even the tiniest movements of the seafloor at a depth of 1 meter below sea level and 12 kilometers offshore. Data collected from April of 2016 through July of 2017 revealed unexpected results. The seafloor remained stable for most of the year but suddenly sank by 4 centimeters over an 8-day span before stabilizing again. Notably, the greatest movement occurred at the base of the volcano, while the summit showed the least activity. If magma inside Etna caused this shift, the movement pattern would be reversed, with the maximum displacement near the volcano's center. Furthermore, the seafloor movement at 12 kilometers off the coast was concentrated along a single geological fault, whereas closer to land, the activity was distributed across 2 fault systems. This evidence suggests that factors other than magma chamber expansion, such as crustal or fault movement, may significantly influence both the volcano's activity and the surrounding geological dynamics. This situation indicates that the volcano's movement originated at sea and then extended upward toward the summit, with no earthquakes recorded during the 8-day period, clearly showing that seismic activity was not the driving force. Instead, the entire process was governed by gravity, as the volcano gradually collapses under its own weight. In fact, the structural integrity of the mountain is literally crumbling from within, a process that accelerates with each new eruption. Let's consider the bigger picture. The entire volcanic structure is slowly outwardly expanding from the top in all directions. Simultaneously, the volcano's lower slopes are sliding downslope at an average of about 14 millimeters per year, while the overall movement of the entire massif toward the sea amounts to only a few centimeters annually. While this shift may seem negligible, the internal stresses building up inside are immense, and that is what truly alarms scientists. Past catastrophic collapses, large sections of volcanoes sliding away in enormous landslides, have occurred on other slopes due to gravity. Such events, which happen roughly 4 times per century worldwide, cause devastating destruction. An Italian volcanologist recently warned that the southeastern flank of Etna is in motion. The question isn't if it will fail, but when. The danger is compounded because even minor earthquakes, deep magma releases, or thick sediments can rapidly accelerate the collapse process. German researchers have confirmed that the slope's movement is entirely driven by gravity, marking a shift from earlier beliefs that magma pressure was solely responsible. The mountain is essentially being pulled down by its own weight, a slow but persistent destabilization. Authorities in Sicily are already revising evacuation strategies for residents living on the lower slopes, aware that the ground beneath them shifts imperceptibly, inch by inch toward the sea. Yet most inhabitants remain unaware, continuing their daily lives in what is effectively a gradually disintegrating edifice. This creeping deterioration is a slow-motion disaster, potentially escalating from a geological curiosity to an outright catastrophe at any moment. While Etna's summit eruptions have become more frequent, with Strombolian fountains, lava flows, and ash clouds, particularly from August to October, these spectacular displays mask the deeper threat. The volcano is fracturing internally, gradually tearing itself apart from within. When the inevitable slope failure occurs, it will not merely be another eruption, but a seismic event capable of transforming the entire region forever. In summary, this ongoing instability is a warning sign of an impending major collapse. The slow but relentless creep of the volcano's structure suggests that a catastrophe could be imminent, transforming a geological phenomenon into a full-blown disaster.